K2-419 AB, almost 900 light-years away from the Earth. Could it have life? Well, here's the answer. Whoa, let's go a little bit slower before. The planet star K2-419a. It has a luminosity value of 1.9 times to 25 watts. The reason we start with these measurements is because it's the most direct property which can be measured for almost all other parameters on this list. Stellar luminosity is the energy emitted per second, meaning it depends on the star's temperature according to its surface area. A very high surface area star with a high temperature will be very luminous, while a very low surface area star with low temperature will not be very luminous. Speaking about temperature, when we mention stellar effective temperature, it's actually the surface temperature of the star, which has value of 3.7 times 10 to the 3 Kelvin for K2-419a. By following the Planck radiation law, we can determine this value. And a star which appears to have a bluish color, a higher wavelength, would be warmer, while a star which appears to have a reddish color, a lower wavelength, would be cooler. No matter the temperature, however, a star can seem more luminous the larger it is. A larger star has a longer radius, so this radius is of 2.0 times 10 to the 8 meters for K2-419a, and it corresponds to the distance from the center to the surface. Its mass of 1.1 times 10 to the 30 kilograms. Again, luminosity is proportional to these parameters.
There is another parameter which is useful in determining not only the star's mass, but also the planet's mass, and this is the radial velocity amplitude. For K2-419ab, it has a value of 67 meters per second. So how is it determined visually? Let's start by noticing how the planet and star both exert a gravitational force on each other, leading each to move in a normal circular pattern or around a central point. This means the star sometimes moves towards and away from a stationary observer, like the Kepler Space Telescope. Due to the Doppler's effect and the fact that the star is so far away, the wavelength of light is received in the telescope when the star is approaching is not the same as when it is going further away. As it goes further, the light is blue shifted, and as it approaches, the light is red shifted. Therefore, using light, we can determine the speed of this back and forth movement, which is radial velocity amplitude. We can also predict a planetary mass using this phenomenon, since a more massive planet will exert a stronger gravitational force on the star, leading to a higher radial velocity amplitude. Another way to determine this parameter is with Kepler's law of periods, which uses a planet's orbital period and semi-major axis, as well as the star's mass, to determine the planet's mass, which was of 1.1 times 10 to the power of 28 kilos for K2-419ab. Knowing the planet's mass, as well as its volumes, using its radius, we can also determine the planet's density, which will be important in determining whether it can harbor life, though more on that later. It's also quite important to measure the parameters concerning a planet's elliptical orbit. First, there is the orbital eccentricity value of 0.63 for our planet K2-419ab. In an ellipse, there is two focal points, which lie on its major axes at equal distances from the center. When these are on the same point, you get a perfect circle. But as they get further apart, the ellipse is stretched. The amount of stretch is the orbital eccentricity. A planet with an orbital eccentricity that is above 1 will go out of orbit, while an orbital eccentricity of 0 will mean a perfectly circular orbit.
The eccentricity is proportional to the orbit's semi-major axis. The semi-major axis is the distance from the center of the ellipse to its vertex. In other words, it's the longest distance from the star and planet's common center of mass to the extremity of the planet's orbit. The semi-major axis could therefore be seen as the length of the two-dimensional plane on which the planet is in motion. However, this plane is not perfectly aligned with the reference plane with which the star is observed. It's always somewhat inclined in relation to it, and this is what is called the orbital inclination, with a value of around 90 degrees for the planet K2-419ab. This also relates to the impact parameter, which is proportional to the distance between the center of the star and the planet orbiting it as seen by a stationary observer. If the impact parameter is low, the planet will block the light of the star for longer and with more intensity. But if it is higher, the planet is not passing directly through the center of the star according to the observer, so its effect on star luminosity will not be as pronounced. For K2-419ab, the calculated impact parameter is 1.2. It must be noted that this value is inaccurate, as an impact parameter above 1 means the planet does not pass in front of the star, which is not the case for a planet. This can be explained by the approximations which are necessary to use the following formula, such as the total transit time times pi being much smaller than the orbital period. For K2-419ab, the planetary orbital period is 20 days, or 1.8 times 10 to the power of 6 seconds. This has been determined by finding the average time between each mid-transit point, meaning each time the planet passes directly in front of its star. And the reason why is that each time the planet passes through the same point, it means it completed one whole revolution around its star, which for Earth takes 365.25 days. It's important to note that this value of 1.8 times 10 to the power of 6 seconds does not correspond to the calculated value of 3.6 times 10 to the power of 9 seconds, though this difference can be explained by the fact that the equation used to find the period only applies with many approximations taken into account, such as the semi-major axis being much smaller than the stellar radius, or the planetary mass being much smaller than the stellar mass.
Now, when observing the normalized light curve, which puts K2-419a's brightness in relation with the hours from K2-419ab's mid-transit, we can determine some final values which were essential in discovering many of the parameters presented previously. For example, there is a total transit time of 1.4 times 10 to the 4 seconds, which represent the amount of time the planet spent in front of the star according to the Kepler telescope. More specifically, if this represents K2-419ab, this is from the moment a silver of its surface blocks a small quantity of light from the star until it disappears completely when the perceived brightness returns to 100% of its value. Now, the full transit time is similar, but this time only consider the time the entirety of the planet is blocking some of the star's light. What it looks like, if this is our planet's sun, it will start right there when the entirety of the planet is blocking the light and will end up right here. Therefore, the time spent in full transit time is therefore smaller at 5.3 times 10 to the 3 seconds. Finally, the change in brightness provoked by the planet when it reaches the midpoint is called the depth. For K2-419ab, this is only 3.8%. For larger planets with smaller stars, this percentage is much more higher, while smaller planets orbiting larger stars have much smaller depth values.
Now that all the parameters have been explained, we can finally answer the ultimate question. Could human beings, or more generally any life form, feasibly live on K2-419ab? Most importantly, we need to first know if this planet is a gas giant like Jupiter or a rocky planet like Earth or Mars. This can be determined using density, and since this planet's density is 6.8 times 10 to the power of 3 kilograms per meters cubed, which is over 1,000 higher than Earth's density, we can be sure that this is a rocky planet. In comparison, Neptune, the densest gas giant in our solar system, has a density of 1.6 times 10 to the power of 3 kilograms per meter cubed. However, K2-419ab might as well just be a floating rock in space if it isn't located within the star's habitable zone, which is between 9.6 times 10 to the power of 9 meters and 2.3 times 10 to the power of 10 meters from the star, so K2-419a. In this area, it is neither too hot or too cold for liquid water to be present, and therefore a possibility of life it's very feasible. And K2-419ab is actually found just inside the zone, being 1.8 times 10 to the power of 10 meters away from the star. Up to date, all signs seem to be pointing towards the possibility of life on this faraway planet, but it's still important to discuss other parameters which affect habitability but are harder to assess using current tools. For example, the surface temperature must be considered using multiple factors. We've already determined that the planet is located in the habitable zone, meaning the temperature resulting from the distance between the planet and the sun should not be too high or too low. There is also, however, the surface reflectivity, which is harder to measure, but can be compared to, let's say, wearing a black shirt or a white shirt on a hot summer day. The black shirt, which would in this case have less surface reflectivity, will absorb light and therefore feel warmer to wear. Finally, the atmosphere should also be considered, as more greenhouse gases, such as water vapor, CO2, or methane, will increase the surface temperature substantially, as it can be seen with global warming on Earth. It's also important that the planet contains these gases in the atmosphere, as without them, the temperature difference between night and day will be too large to allow any life forms to sustainably survive. In fact, atmospheric composition is important. The presence of gases such as oxygen could show signs of cellular respiration, and an adequate percentage of nitrogen should also be found to ensure consistent atmospheric pressure. To determine this atmospheric composition, we use telescopes such as Hubble, since they can detect the wavelength of the light, which is not absorbed by a planet's atmosphere on its way to reach the telescope. By using a spectrograph, scientists can discover which wavelengths have been absorbed by the planet's atmosphere and compare this data to the wavelengths absorbed by gases in Earth's atmosphere. We should also note that the intensity of seasonal variations will be determined by the orbital eccentricity parameter we mentioned earlier. According to NASA, K2-419 orbital eccentricity is 0.042, which is higher than Earth's orbital eccentricity of 0.017 by a factor of around 3. This doesn't disqualify the possibility of life, but means that it will have to adapt to very cold winters when the planet is furthest from the sun. Finally, we need to consider protection from the dangerous rays produced by the star, thanks to a magnetosphere, for example, which can deflect deadly solar radiation. This requires metals such as iron in the planet's core, so we would have to see if this is present in our planet. So not all relevant data is available to be certain. Whether K2-419b is capable of life, there's still many things that point to its possibility. But before you think about moving there to escape global warming, just keep in mind you've got a long 900 light-year trip ahead of you.